for instance, we have three real numbers, A, alpha, and gamma, and we know that gamma, sorry, not gamma, alpha is greater than 0, right? Then x minus a to the gamma plus alpha is small o of x minus a to the gamma when x goes to a, right? Because the limit when x goes to a of x minus a to the gamma plus alpha divided by x minus a to the gamma, right, is just the limit when x goes to a of x minus a to the alpha, right? But x minus a alpha is greater than 0, so the limit of a polynomial, right, in this case, is going to be 0. Okay. So in practical applications, this means that, for instance, x squared is small o of x, or x cubed is small o of x squared, right? And also here you see small o of x squared, this is small o of x, so this is small o of x, so that means that x cubed is also small o of x. Sorry, this is when x goes to 0, right? Right, so that what this means is that x squared and x cubed and every other higher number x to the alpha when alpha is greater than 0 are small o of x. That means that they are going to 0, right, much faster than x. So you have here, if you think about the parabola goes like this, right? So they're approaching 0 much faster than the line, right? So that's how you need to think about these things, right? This is going to be very useful for computing limits, but also for many other purposes, right? Okay, so let's go for the next example. So we have alpha, again, a, alpha, and gamma real numbers, and we have alpha greater than 0, so we have 1 over x to the gamma plus alpha is small o of 1 over x to the gamma when x goes to a, right? Why? Because the limit when x goes to a of x to the gamma divided by x to the gamma, so this is when x goes to infinity, sorry. When x goes to plus minus infinity, yes. X to the gamma plus alpha, no, sorry, yes. Plus alpha is in the denominator, right? This is 1 over x to the gamma plus alpha divided by 1 over x to the gamma, so this is going in the denominator, sorry, in the numerator. So this is the limit when x goes to, and this is plus infinity or minus infinity of 1 over x to the alpha, which is 0. Okay? So again, in other words, this means that 1 over x squared, for instance, is small o of 1 over x when x goes to plus minus infinity, right? Because that means that 1 over x squared goes to 0 much faster than 1 over x, and so forth for 1 over x to the 4th is small o of 1 over x, and so forth. Okay? Okay, let's see some more examples. We have that the sine of x is small o of the square root of x when x goes to 0. Okay, so we know that the limit when x goes to 0 of the sine divided by the square root of x, we know that the sine is approximately equivalent to x, right? So this is the same as the limit when x goes to 0 of x divided by square root of x, which is, in other words, the square root of x. So this is 0, right? So this is because the sine is approximately equivalent to x, right? We know that this is approximately equivalent to x when x goes to 0. Then it means that we know x is small o of the square root of x, right? When x goes to 0, just like what we were saying before, right? That x to the gamma plus alpha is small o of x to the gamma when x goes to 0. So in this case, we have gamma equals 1/2 and alpha equals 1/2, right? this translates into x equals small o of the square root of x when x goes to 0, right? And so x is small o of the square root of x, and also is a sign, right? Because both of them are asymptotically equivalent. Right? So if two functions f and g are asymptotically equivalent, as we have been saying before, then that means that how to formalize this using small o is that we can say that f is equal to g plus small o of h, right? When x goes to a, when x goes to a, right? Or in other words, that f minus g is small o of h when x goes to a, right? So that means that the difference between f and g, or f and g are similar up to function h that we can determine, right? Then that's what the things that we will see when we develop the Taylor polynomial, right? But this is kind of how you write about asymptotic equivalences with this notation. Right? Okay, so another couple more examples. 1 minus the cosine of x is small o of x, right? When x goes to 0. Because the limit when x goes to 0 of 1 minus the cosine of x divided by x, we know that 1 minus the cosine is approximately equivalent to x squared divided by 2, right? So this is 1 minus, so it's minus, it's 1 minus the cosine. No, yes, sorry. 1 minus the cosine is equivalent to x squared divided by 2 divided by x, so this is the same as x divided by 2, so the limit of this is going to be 0, right? So again, 1 minus the cosine is asymptotically equivalent to x squared over 2 plus small o of x. Okay, this is what this means. Right? Okay. Okay, let's see a last example. Well, from the asymptotic equivalences and negligible relations that we had seen before, so we know that the logarithm of x to the r is negligible in comparison with x to the q. Well, that means that the logarithm of x to the r is small o of x to the q when x goes to infinity, right? Now the same goes for x to the q is small o of a to the x for any a that's positive and greater than 1, obviously, and this q and r positive numbers, and a to the x is small o of x to the x, right, when x goes to infinity. So you see how to write the things that we have seen in terms of negligible functions and asymptotic equivalences using the small o notation.